have been discussing about lasers in the last couple of lectures, and we have covered almost everything to deal with continuous lasers. In this lecture, we will be doing the last part of the lasers which are necessary for our course, which is going to be the pulse lasers. So, until now we have been focusing on continuous lasers, the principle of lasing and all that. Now, we are going to look at continuous versus pulse lasers. So, what we have looked at has been excitation of the lasing atoms or molecules by using external sources of light or radiation, for example, flash lamps or another lasing another laser which is pumping, by using electromagnetic radiation or other things, but basic idea has been pumping. The output of the laser light can be a continuous wave, as we have been discussing, if the pumping is continuous, or pulsed if the pumping is pulsed. Now, this is the second part which we are going to now look at. Most of the cases until now has been continuous, and so the pumping part in our case could be of various kinds. The pulse lasers have very high intensities because the laser intensity is concentrated in a very short time duration, and that is one of the critical reasons for studying this part, because this is the one which gives rise to nonlinear optical properties. So, there are two ways of looking into quantum computing and quantum related aspects. One is in the linear region, which is very easily possible with the continuous lasers and principles that we have been looking at. Also, under the condition where the photons are very low in number, which is low photon count regions, where we would like to actually have very low number of photons to be dealing with. So, that is one kind which we have almost done now, but the other kind where we would like to deal with a lot of photons, possibility of having a lot of them simultaneously, so that it can induce events or phenomena which are not possible to be explained by under the linear domain. That is the part which we are necessary to have short time pulses and other kinds of things. Also, for measuring time scales which are very short, and so this is the region where we are now entering, which is pulse lasers. Nonlinear optics is one of the things which we have been looking at. So, what is it that is important for the continuous versus ultra short pulses of light? The continuous beam, for instance, if you look at it with time, is constant, whereas and it gives a spectrum which is ideally a single frequency, but we know that it has some very small bandwidth, whereas on the other hand, an ultra short pulse, again with a very short time window, has say constant frequency in the ideal case. A constant and a delta function, which are basically Fourier transform pairs, is what we have in the ideal scenario. But in reality, this is what we have. We have the irradiance versus time for a long pulse can be looked at a very narrow spectra in the frequency band, and vice versa. A very short pulse in time corresponds to a very wide frequency or a energy band in the frequency spectrum. So, by using the Fourier relation between the two, which is also the same as the uncertainty principle, which states that the two are transforms of each other in time versus frequency, and so whatever is long in one domain is short in the other domain. In the, as we mentioned in the last slide, it is sort of like the extreme cases where we have continuous versus a line versus a continuous. In reality, it is some width with respect to a very narrow width, again a short width with respect to a long width. That is what we are looking at. So, the laser time bandwidth relations therefore can be summarized in this slide, as we have said. For a continuous wave laser, we have roughly a single frequency which corresponds to a delta function in wavelength or frequency, and an ultra fast laser pulse is therefore a coherent superposition of many monochromatic light waves within a range of frequencies that is inversely proportional to the duration of the pulse. So, for instance, a 10 femtosecond pulse width, femtosecond is 10 to the minus 15 seconds, corresponds to say in wavelengths 94 nanometers around the center frequency. This is a titanium sapphire laser. So, it has say 800 nanometer center frequency, and so that is how this is a commercial laser, and we will discuss that in a minute. So, that is how the relation works for the time and frequency, and this is known as the time bandwidth relationship, which will be very useful when we are in this domain of ultra short laser pulses. So, what is the main difference here between, let us say, a wide band source, for instance a light bulb, which is also broadband, but as we have discussed many times over and over again, sources which are not going to have coherence or anything to do with stimulated emission are not going to be relevant in this picture. So, a light bulb is the kind of scattering or spontaneous emission process which is sort of like illuminating me, but for a ultra short laser pulse we need something which is coherent, and so we need something called a mode locked system. So, we have already shown you a spectral features where we had several modes, longitudinal modes present within the mode of the laser being measured, and so within the profile of the laser. And so, once we are talking about locking all the modes, what does it mean to how do we go about doing that? That is what we have to look at. So, in order to look at these pulses, we have to also recognize that they have to be measured in a very particular way. So, the laser pulse characteristics in these cases are done in typically two ways. One is to note the spectral width, which comes from a monochromator. And so, for example, in this particular commercial laser that we were discussing, 800 or 790 nanometer center frequency, we have a bandwidth which is associated to the measurement made in a spectrometer, monochromator, whereas for in time with pulses which are so short, it is not possible to measure it directly. So, it is either measured by using a autocorrelating system or a cross correlating system, but generally the first principle is to use an interferometric way of measuring a correlation between the pulse and itself, and that is one of the ways it is measured. And you can see in this particular case the pulses which are separated at certain distances are being measured by delaying one pulse with respect to the other, and you can see how the interference pattern and fringes look like. If you make squared measurements where the detector actually does a squaring of the system, then you can pick up the interference between the two fields, and so it could be interferometric autocorrelation, or which could be of two types. One is the field autocorrelation, which looks like this, or it could be intensity autocorrelation, where it looks like this, square of what we are looking at, the field autocorrelation, and so on and so forth. So, the Fourier transform in infinite chain of pulses can be written in terms of how it looks like, where the single pulse and the time between the pulses, the convolution theorem can be used, and what we can look at is that there is a frequency band over which these different frequency components can appear in the Fourier domain. Chain of pulses results from a single pulse bouncing back and forth inside a laser cavity of round trip time t. The spacing between the frequencies is called the laser modes, and that is the one which is given as 2 pi over the round trip time t. So, that is why the delta nu, which is the separation between these pulses, are these modes which we are looking at, which is this. So, that is generally what is the situation which is happening, is that we have these round trip times within which the pulse is rattling around the the light is being rattling around within the amplifying cavity, and that is what we are measuring when we look at the pulses which are coming out. So, mode locked pulse train therefore has this field which has this profile, whereas a train of short pulses have this particular for the as we just mentioned. This is what we just looked at. When we have non mode locked pulse train, then we have a random phase for each mode, and so the overall function essentially has as summation of all these different modes, which is quite difficult to ascertain, and they can be all over the place. So, there is a they can have beating and all kinds of things. However, all of this then does not happen when you are looking at it in the mode lock condition, where the phases are all the same. So, the basic idea about the non mode locked versus mode locked is that the phase distribution is fixed for the mode locked pulse train. So, here is the pictorial output of what we are looking at. Locking the phases of the laser mode yields an ultra short pulse, and that is the mode locking. So, if you have random phases of all the laser modes, it is like this with radiance with time, and it is similar to what we have in case of the light bulb also. So, the phases are all random, whereas when they are all of one kind, they are all in phase with each other, then the period of time when they are all in phase gives rise to the time over which all the locked phases are there. So, all these other unlocked phase conditions are not possible to be seen, only the ultra short period of time over which all the phases are in, all the laser is in time, is in phase, is the one which is being looked at. So, this is the ultra short pulse during which all the phases are the same. So, here is how it looks like. Then there is all these different modes that we are coming out from the laser. This is the resonator round trip time, and as the modes get to have the same phase, they overlap and they get amplified more and more at these points with respect to the time where they are not in phase, and so they randomly are all over the place. So, statistically, so they average out, whereas the amplified ones are the ones which are happening exactly at the laser round trip time, and we get the locked modes at those places. So, you can actually go ahead and do numerical simulations of mode locking to see how you can have different time frames of these modes appear exactly locked at a given period of time, and you can have the very short period of time over which all the modes are equivalent, and the rest of the time they are not there. So, if you have, for instance, you can do it for simple 8 modes, you can do a simulation, and here it is showing an example case where the phases are 0 at time equal to 0, but at other times whenever they are in phase, have a fixed phase between all of them, then they come together and for a very short period of time, and that is the ultra short pulses for me. However, if they are always random, then there is no time possible where they will all get amplified simultaneously to give rise to that short period of time. So, ultra fast lasers often have thousands of modes. So, a generic ultra short pulse laser has a broadband gains media, a pulse shortening device, and 2 or more mirrors. That is typically the case. This pulse shortening device is known as a mode locker. So, there have been many pulse shortening devices which have been proposed and used over the years. So, one quick option is to actually use pulse pumping. So, instead of using a pulse shortening device, if you already have a pulse pumping device, then pumping a laser medium with a short flash lamp yields a short pulse. Flash lamp pulses as short as 1 microsecond can exist. Unfortunately, it yields a pulse as long as the excited state lifetime of the lasing media, which can be considerably longer than the pump pulse. Right. So, that is one of the issues here. Since the solid state laser media have lifetimes in the microsecond range, it yields pulses of microseconds to milliseconds long. So, so this is typically how it looks like. These are long and potentially complex pulses that come out from partially from a laser which is being pumped with the pulse laser. So, this is based on the pulse pumping idea. There is no mode logging device inside the laser in this case. There is another approach which is known as Q switching. Q is typically known as the quality factor, and so this is what it is done in case of lasers like this. This is a Q switching involves preventing the laser from lasing until the flash lamp has finished the flashing and abruptly allowing the laser to laze. The pulse length in this case is limited by how fast can we switch and the round trip time of the laser, and yields pulses of 10 to 100 nanoseconds long. So, this is basically based on the idea that you are building up the cavity within the building up the gain within the cavity, and then at a certain point of time you just let the system switch so that the output can go up, output can go, and then you get the pulse. So, it is a switching system. This is the Q switching. So, how do we Q switch a laser? For example, a Q switching involves preventing a lasing until we are ready. So, a typical Q switching system is a Pockels cell which switches in a few nanoseconds from a quarter wave plate to nothing. So, a Pockels cell is a basically a wave plate which is set at 45 degrees. So, wave plate is this is a roughly a quarter wave plate which is placed, and so light becomes circular in its first pass and then horizontal in its next, and then is rejected by the polarizer in this particular case. So, basically whenever we have this lambda over 4, so it goes through, first time it becomes circular, it comes through here, and then it is having the opposite polarization of the incident one, and so it rejects and it comes out. So, the wave plate is with respect to that. After switching, light is unaffected by the Pockels cell and hence it is passed by the polarizer. So, the Pockels cell is something which makes the material undergo a lambda by 4 shift when it wants to switch it, otherwise it remains it does not do anything to the light coming through, and that is how it acts as a switch. So, so that is the basic idea behind Q switching. Now, there are different ways of looking at mode locking. So, until now we have not looked at mode locking yet, we have been looking at the gain modulation process as to how to do this. Now, passive mode locking, there can be two different kinds, one is the passive mode locking and the other one is the active mode locking. So, in case of passive mode locking, the idea is to use something called a saturable absorber, which means that an absorber which can keep on absorbing until it gets saturated when it does not absorb anymore. So, like a sponge, an absorbing medium can only absorb so much. High intensity spikes burn through, low intensity light is absorbed. So, it is like it is an intensity gating in that sense, that beyond a certain intensity it just lets it go. So, that is passive mode locking principle, for example. So, here is the effect of a saturable absorber. First, imagine the raster scanning of the pulse by time, for instance. So, with the passive mode locking, you can almost act it like a gate. So, for example, here is the case which is shown of a saturable absorber. So, let us consider that we are looking at the pulse at every point of time. What we see is that the weak pulses are being suppressed and the strong pulse shortens as it gets amplified. After many round trips, even a slightly saturated absorber can yield a very short pulse. So, that is one way of looking at how you can generate a short pulse like this. Again, looking at passive mode locking, whenever we have high intensity spikes because of this principle of letting the system go through this idea of intensity which can be only high intensity which can go through, and there is this spikes where the laser can output, and so the gain goes through a dip and it again goes up, goes to a point where it reaches the maxima, and then again it goes through the saturable point where it can get out of the system and it keeps on going. So, this is basically the principle of creating a short pulse. This was actually one of the first ones which were used for producing very short pulses. It can have different effects when you have a slow saturable absorber versus a fast saturable absorber. If the absorber responds slowly, more slowly than the pulse, then only the leading edge will experience pulse shortening. This is which is the most common scenario, unless the pulse is many picoseconds long. The gain saturation essentially shortens the pulse trailing edge, and so the leading edge becomes faster, and the reducing gain is available for the trailing edge of the pulse and for the later pulses. So, there is this particular overall curve that you can look at when you have this initial loss versus gain, and you can see that basically the peak pulse is getting amplified more and more, where the mode locking is going to be achieved and the tails are getting attenuated. So, the combination of saturable absorption and saturable gain yields short pulses even when the absorption is slower than the pulse. So, this is one of the idea, and so this was first applied for dye lasers, where the gain media, which is a dye laser, was and the advantage of using it for a dye laser was because that the dye laser had the capability of a very broad spectral condition. So, this is one of the things which we mentioned about dye lasers, that they had a very wide absorption, and that is the advantage of using this. The passively mode locked dye lasers yielded pulses as short as a few hundred femtoseconds. They are limited by ability to saturate the absorber. So, if you can have a fast enough absorber, then all the combination of the processes that we mentioned, it was possible to do this kind of results. So, here are some of the dye lasers which were used for producing the initial short pulse lasers. In fact, the Nobel Prize which went to Zuel, who is no more, for demonstrating the first very short time dynamics was incidentally using these kinds of lasers, dye lasers, which were able to go down to very short pulses. And this is essentially the first of its kind which were used, which was a ring dye laser, where the pulses were made to collide, and higher intensity of the saturable absorber is what was being used. So, it is called a colliding pulse mode locked laser, where two pulses colliding resulted in even shorter pulse, and that was one of the principles which were used to get better shorter pulses. So, this is the one which was originally used to produce very short pulses, sub 50 femtoseconds for the first time, which were then shortened further to produce the real fast dynamics measurements, which were finally led to many other important developments. So, the other approach where, or other principle which has really helped in terms of generating short pulses, is the idea of the fact that many materials actually behave like lenses. So, a lens can be something which has which is due to the phase delay which can be seen. The beam varies with the distance that we know, and that is how we get a lens, the effect of that. However, there can be medium which can undergo where the length is constant, but its refractive index varies with the distance, and that can also act like a lens. In both cases, a quadratic variation of phase with distance yields a lens. And so, this is the second principle of this has been seen of late to be giving rise to a lot of mode locking principle, and that is the Kerr lens principle, which is used in solid state lasers of today, which gives rise to this phenomena of producing short pulses. And this is the mechanism which is used in the most popular laser of today, which is the titanium sapphire laser, titanium being the active material in this sapphire crystal, where this nonlinear process of refractive index, which is which at high powers give rise to an additional focusing effect, which limits the available zone over which the system can keep on going back and forth. So, it sort of like works like a very sharp aperture, so losses are too high for low intensity CW mode to laze, but not for high intensity femtosecond lasers. So, this acts like a very sharp aperture through which only the peak of the intensity can go through, producing a very short pulse. So, it is a type of a saturable absorption in some sense, where pulse experience additional focusing due to high intensity and the nonlinear refractive index, then we align the laser for this extra focusing, then a high intensity beam would have a better overlap with the gain medium, and this is a type of saturable absorption which is used for the case of titanium sapphire laser. This additional focusing optics can arrange for perfect overlap of the high intensity beam back into the sapphire crystal, and that is what is being used for this particular purpose. The low intensity beam unfortunately does not add the advantage, and so it gets lost, and so only the high intensity beams survive and finally produce the short pulses. So, here is a example of how this mode locking works for a saturable absorption being generating through Kerr lensing, and so this is a model of the idea as to how it happens, and mode locked laser is seen which has a wide bandwidth and a short pulse. So, it is the currently, as I mentioned, sapphire is the currently the workhouse laser for most of the ultra fast community, emitting pulses as short as a few femtoseconds and average power in excess of a watt and more. So, it has this wide bandwidth which is necessary for this kind of a short pulse operation to happen. So, it is this near infrared region which is what is being used. It ranges lasers from 700 to about a micron. It has a very nice lifetime also of the excited state, which lets it to remain inverted for quite a while. It is a 4 level amplifier system, as I mentioned before. So, so what we have learnt here is that so here is the principles that we have learnt here. We have the components of the laser system is like this. What we are trying to do in this process is we are going to lock the cavity modes in such a way so that only for a brief period of time they overlap to get the maximum gain, which is a mode locking mechanism, and this is additionally helped with the help of dispersion compensation. And in case of mode locking, we realize that only at a very short point of time there will be an in phase locked phases for all of the pulses, giving rise to the short pulse. Otherwise, they are random and therefore they go away. The bandwidth results in this point over which the pulses will be wide, and as the narrow spectrum, it will start getting broader, the pulses will get mode locked, and you will get a broader and broader spectrum. And finally, when all the pulses are the shortest possible, you get the maximally broadened spectrum. So, this is the broadest spectrum for the shortest possible pulse. That is the basic idea behind this principle of ultra short pulses. That is what we have learnt. This is the bandwidth we are looking at it, and this is the time width that we are looking, and what we have found is that delta nu delta t is constant. So, irrespective of what we do, when we have a shortest pulse, we have a long band of the pulses. We have looked into the different mode locking mechanisms, active versus passive. The active ones actively modulate the gain in the medium, or it could be something like a pump which is already changing, it is pulsed, that is a synchronous pump mode locking. The other one is to use an acousto-optic modulator, which is a loss modulation kind which does that. The other one which is these are active, as the other case is the passive mode locking, which is a saturable absorber like dye, solid state, and the optical Kerr effect that we have mentioned. So, the outputs are of these different kinds which we mentioned: CW versus CW mode locked, Q switched, Q switched mode lock. All 4 possibilities exist. The Kerr lensing one we discussed in detail because that is the one which has been used in detail nowadays. The Kerr medium is our sapphire crystal that we use in titanium sapphire, for instance, and the high intensity ultra short pulses are the ones which are the ones which survive in this process. The focus pulse is going through this high intensity profile, only the ultra short pulses survive, the rest do not. The intensity dependent refractive index is the one which helps in this process. It creates spatially self focusing condition as well as the temporally self focusing condition, which is due to pulse shortening due to group velocity dispersion, and this is the loss modulation with saturable placement of gain medium and then hard aperture, which is coming due to the intensity dependent refractive index. So, here is a cartoon which shows that the refractive index depends on the intensity of light, self phase modulation due to temporal intensity, due to transverse mode profile, and in as it goes through, it produces this chopped short pulses, which are then stretches, which is sort of stretched because of the group velocity dispersion, which is provided due to this process, and one can have it shortened by using other process of compensating for the group velocity dispersion, because it is a linear process, and we can get as short as 6 femtoseconds, 5 femtoseconds in these kind of processes. So, the compensator can be simple as a prism compensator, can basically go through the wavelength tuning mask. This is the bandwidth part where we are essentially making sure can be compensated. So, it goes through these prism systems where the amount of linear frequency chirps are compensated by this process. So, these are the components of the ultrafast system: shortening mechanism, dispersion, compensation, and the starting one was the process that we mentioned. It can also have many other processes like saturable absorber and cavity perturbation and all that. In a Tie-Sapphire laser, which is the one which is most important today, is it has a typical cavity as shown here, which is inside an oscillator, which is then compensated with the help of a prism pair, the dispersion, and it is applied for many different cases. The output coupler comes through the laser. It can be further amplified by using the principle of linear gain, where it is done is that the oscillator is put through a linear stretching device which makes a longer pulse. It is then put through an amplifier where it is again amplified in this process, and then a compressor would then decompress, which again compresses the system of the amplified pulse to get even higher intense pulses. So, here is the typical chirp pulse amplification principle that we have of today. It is the oscillator which first produces the short pulse, initial short pulse, which goes through an chirping process to stretch it, and then the low power safe for amplification goes through amplifiers, and then high energy pulses have done through amplifier, and then a second grating pair reverses the dispersion of the first pair. So, this is the first reversion part which lengthens the pulse, and here the second pair essentially compresses it, and it results finally in a high intensity ultra short pulses. So, femtosecond pulses can be amplified to petawatt powers. These are so intense that electrons can be rapidly stripped from atoms. So, we have used principles where we have also used the idea that the modulation of light induces the beam narrowing, and all these principles were used for mode locking, as we just mentioned. We mentioned modulation directly or externally by using different principles, and a typical external modulation was to use the CW laser light and modulation, which are also done in fibers and other kinds of optical sources. The femtosecond lasers thus amplified can be taken to petawatt powers, which can be so intense that can strip electrons rapidly from atoms. With this, I am going to end this lecture, because whatever we wanted to do in terms of lasers, in there being a continuous source for the kinds of operations that we are interested, or as source where we can actually use them for timed measurements or inducing nonlinear processes, have have all been looked into in this lecture. With this, we end this entire look into the lasers and their required ideas behind it. In the next lecture on, we will be using them for further applications into quantum computing. Thank you.